Hello and welcome back. In this video lesson, we're going to look at eigenvalue dominance and decomposition. So one of the things we've already described or seen that if you repeatedly multiply some vector by a matrix A over and over again, it performs a geometric transformation. It rotates and scales that vector. But one of the things we noticed in the last lesson is that repeated multiplications by A cause that vector to rotate in the direction of the eigenvector whose eigenvalue is the largest in magnitude. So we're going to provide some justification for why that happens. So for an n by n matrix A, we know we're going to have n eigenvalues, lambda 1 through lambda n. And we're now going to label them in descending order of magnitude. So notice that we have absolute value signs. So for example, if we had an eigenvalue of -10, let's say, then we would say that -10 is the dominant eigenvalue provided that all the other ones were smaller in magnitude. So this could be like a 3, and technically 3 is larger than -10, but if you take the absolute value and you just look at the magnitude, -10 has a magnitude of 10, 3 only has a magnitude of 3. So we're going to just label them with this convention in descending order to make them easier to organize. This isn't a hard and fast rule, it's just something that we tend to do. That way we can always say lambda 1 is the largest magnitude eigenvalue. So the eigenvalue with the largest magnitude, the largest absolute value, is called the dominant eigenvalue. And we're going to make the following claim. When we multiply some vector repeatedly by a square matrix A, that is a to the t power times x naught, then as t approaches infinity, that is as we make that power really, really large, the resulting vector, which we'll refer to here as the output of that, we'll call that b for the moment, b equals a to the t times x naught, rotates/stretches in the direction of the eigenvector corresponding to the dominant eigenvalue. That is, if v1 represents the eigenvector of the dominant eigenvalue, then we can say that as t approaches infinity, the limit of that multiplication results in something that approaches v1. And let's now provide some additional justification for that. But furthermore, as this vector continues to get multiplied by A, that is stretched, rotated, after t becomes really large, the initial vector gets closer to the eigenvector, so the eigenequation AV equals lambda v takes effect. So imagine that this vector x naught, that after repeated multiplications points in the direction of the eigenvector, now additional multiplications by A cause that multiplication to produce a scalar multiple of that eigenvector. And so the only remaining alteration that will take place on this final vector v is the scaling effect of lambda. If lambda equals 1 is the dominant eigenvalue, then the resulting vector will reach a steady state and will not change. So here is an example. The matrix A equals 3, 0, -1, 2 is the transformation matrix for some initial vector x naught equals xy. We demonstrate that this vector will rotate in the direction of the eigenvector corresponding to the dominant eigenvalue, and once there, will only become scaled by the dominant eigenvalue for all further multiplications by A. So here are the outputs, and we're going to use our applet from our last lesson to show this. Lambda 1 is equal to 3 is the dominant eigenvalue, and so this one is dominant. And this means that eventually, once we multiply our initial vector by A enough times, that vector is going to rotate in the direction of 1, 0. So what we're saying essentially is that it doesn't matter what eigenvector or what vector you start with, provided that it's not already an eigenvector, but that progressive multiplications by A will cause this vector to rotate. So if this is my x naught, then multiplication by A, maybe one time, will rotate and stretch it a little bit, but ultimately this vector will rotate in the direction of the dominant eigenvalue, which is in the direction of 1, 0. So what we're saying is that if we take A to a large enough power and multiply it by x naught, what we will get approximately is lambda 1 times v1, or some multiple of lambda 1. So I should probably say some multiple of lambda 1. So that is, eventually it will rotate enough and stretch enough to become rotated in the direction of 1, 0, and then it will just continue to stretch in that direction. So let's go ahead and take a look at the applet that's going to demonstrate how this works. So here we have the applet pulled up, and what I have entered in here is the initial matrix 3, negative 1, 0, 2, and I'm just going to start off with this arbitrary vector 2, 1, which you can see is both the red and black vector. The red vector will stay there as a reference, or the black vector will stay there as a reference so we can see what happens. So when I multiply by a one time, so this is a to the first times the 2, 1 vector, basically one multiplication by a will cause this 2, 1 vector to rotate a little bit, and notice that it's become scaled as well. If I do it again, and let me just show these two things here. Ratio of y to x and a to the first times x. So the y value that we would get is 2, the x value is 5. You can see that that vector is 5, 2. So the ratio of 2 to 5 is 0.4. And the multiplier, so a to the first times x gives me 5, 2. And then if I do it one more time, if I drag the slider to t equals 2, I'll get the vector 13 to 4. 13 and 4, which is this vector that I would get if I push this over one more time. And you can see what's happening here now. A squared times the initial vector produces 13 and 4 as its components. That's the components of this red vector, with the ratio of y to x of 4 to 13, which is 0.31. If I continue to do this, watch what happens to that vector. It's progressively rotating in the direction of the dominant eigenvector with the largest eigenvalue. So you can see at this point that a to the 17th times that initial vector produces this ugly vector here, 1, 2, 9, 2, 7, 1, 2, 3, 5, as the x component, 1, 3, 1, 0, 7, 2 as the y component. Now that may not seem like a 1 to 0 relationship there, but you can see that if I divide the y component by the x component, the rise to run of that vector is pretty much 0. So we can see that this is essentially a relationship of 1 to 0. Not exactly, but you can see that this top number is much, much larger than this bottom one. And you can see that what happens eventually is that vector becomes even closer to 0. And what we should see is that the additional multiplications cause this vector to become larger by a factor of 3. So to kind of summarize that picture, here's the one that we started off with. This was when we had a to the 0 times the 2, 1 vector, which a to the 0 times the 2, 1 vector is just the 2, 1 vector. But then eventually when we make the power large enough, we can see that that vector, that red vector, is pretty much in the direction of 1, 0. And if I multiplied it again by a repeatedly, I would see that basically this vector just gets tripled because now it is in the direction of the dominant eigenvector. And let's just show that it didn't really matter that we picked 2, 1. We could have picked something else and it still would have happened. So let's show if we, for example, picked the vector negative 0.5 and positive 2. Okay, there's our initial vector. Oops. So watch what happens. Right now, our vector points in the direction of negative 0.5, 2. And if I multiply it by a one time, you can see that that red vector kind of rotated to the left, but as I continue multiplying it repeatedly, it again, notice, points in the direction. Now 1, 0 is to the right, but still, even this vector right here, negative 87, blah, 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 and the y component being that, that's pretty much a multiple of the 1, 0 vector. Once again, it's just a negative multiple of the 1, 0 vector. And we see that it still points along the x-axis. Negative 1, 0, remember, is also an eigenvector. If 1, 0 is an eigenvector, that just means that the y component has to be 0 for it to be considered an eigenvector. We can see again that thing rotates in the direction of the dominant eigenvector with a scalar multiplier of about, right now it's about 2, but that's only because my power is not large enough. If I made this slider go up to 100, we would see that the relationship between like a to the 100th times x naught and a to the 101st times x naught is there would be a multiplier of 3 there. So let's go ahead and explore mathematically why this happens.